The cosmic mystery. When stars refuse to obey Newton's laws. Close your eyes for a moment. Imagine standing beneath a night sky so vast and infinite that your mind struggles to grasp its dimensions. Above you, billions of stars dance in patterns that have captivated humanity for millennia. We have built entire civilizations around understanding these celestial movements. We have launched our greatest minds into the pursuit of cosmic truth. Yet tonight, we gather to explore something that unsettles even the most brilliant physicists on Earth. The universe is not behaving as our mathematics predicts it should. Welcome. Before we begin this journey into the invisible architecture of existence, subscribe to the Relaxing Science channel. Give this video a like and share with us your location and the time where you are listening right now. Your presence transforms this solitary exploration into a shared moment of wonder. Consider a simple scene from our cosmic neighborhood. Observe a galaxy spinning through the void of space. Picture its elegant spiral arms, rotating with graceful precision. The outer edges of this galaxy contain stars that are impossibly far from the galactic center. According to the laws that Isaac Newton discovered and that Albert Einstein refined, these distant stars should be moving much more slowly than they actually are. The gravitational pull from the galactic center should be so weak at such vast distances that these outer stars would gradually drift away from their orbits, escaping into the cold emptiness of space like leaves blown from a tree in autumn wind. Yet this does not happen. The stars remain bound to their galaxies. They maintain their velocities. They continue their cosmic dance as if held by invisible hands. When astronomers first observed this phenomenon in the 1970s, they faced a profound choice. They could accept that the mathematics upon which physics rests, the very foundation of our understanding of reality, was fundamentally incomplete. Or they could continue believing in the mathematics and propose the existence of something that had never been directly observed, never been touched, never been definitively measured. They chose the latter path. They named this invisible substance dark matter. The story of dark matter is not merely a scientific tale. It is a narrative about the limits of human knowledge, about the courage required to believe in something you cannot see, and about the eternal dance between observation and theory. It is about how science builds elaborate structures of understanding upon pillars of mystery. It reveals something profound about the human condition, our desperate need to explain the unexplainable, to find order in apparent chaos, to create certainty from uncertainty. Throughout this exploration, we will move through layers of understanding. We will begin with the foundations of gravitational science, examining how Newton and Einstein taught us to see the universe. We will then confront the observations that challenged these teachings. We will explore the invisible substance that scientists propose fills most of the universe. We will examine the technological endeavors to detect what cannot be seen. We will contemplate the philosophical implications of believing in the invisible. And finally, we will stand together at the frontier of human knowledge, acknowledging the mysteries that remain. Each section builds upon the previous, creating a tapestry of understanding that grows richer as we progress. The journey ahead is not one of simple answers, but of deepening questions. It is an invitation to think like a scientist thinks when confronted with the incomprehensible. It is a moment to pause and breathe and allow your mind to expand into the vast spaces we will explore together. The universe, in its infinite complexity, has always revealed its secrets slowly. Ancient astronomers watched the heavens with naked eyes and created the first maps of the stars. Medieval scholars preserved knowledge through dark ages. Renaissance thinkers dared to question established doctrine. Newton revolutionized physics with mathematical precision. Einstein showed us that space and time were not absolute, but relative, woven together in a cosmic fabric far stranger than anyone had imagined. And now, in our modern era, we continue this tradition of discovery by pursuing something that eludes our most sophisticated instruments. Dark matter comprises roughly 85% of all matter in the universe. Let that number settle into your consciousness for a moment. Everything you can see, everything that emits light or reflects light, everything composed of atoms and molecules and stars and planets and living creatures represents only about 15% of the matter that exists. The overwhelming majority of material reality is invisible to us. It does not emit light. It does not absorb light. It does not reflect light. It interacts with the universe primarily through gravity alone. This realization transforms how we understand our place in existence. We are not the primary constituents of reality. We are not even the majority. We are, in a profound sense, the minority inhabitants of a universe dominated by something we do not understand and cannot directly perceive. This is humbling. This is also beautiful. It reminds us that the universe is vastly stranger and more wonderful than our everyday experience suggests. As we move forward into the deeper layers of this mystery, remember that you are not alone in your confusion or wonder. The greatest minds in physics struggle with these questions. They debate, they propose, they test, they revise. They remain uncertain, and yet they continue. They continue because the pursuit of understanding, even when that understanding remains incomplete, is fundamental to what makes us human. We are creatures driven to know, to comprehend, to solve the puzzle, even when we suspect the puzzle may be larger than we can ever fully grasp. The night sky above you contains secrets waiting to be contemplated. Those stars you see are not the whole story. Around them, through them, binding them together in invisible embrace, flows the dark matter. We cannot see it, but its effects are everywhere. Its influence shapes the structure of galaxies. Its presence determines the fate of the cosmos itself. And in exploring this invisible reality, we explore something fundamental about existence itself. The foundation, how gravity shaped our understanding of the universe. Let us travel backward through time for a moment, not with a time machine, but with our minds and imagination. Picture a garden in England sometime in the year 1666. A young man sits beneath an apple tree. He is thinking about motion, about forces, about the invisible connections between objects, separated by empty space. This man is Isaac Newton, and the thoughts he is having will transform human civilization forever. Before Newton, people understood gravity only through experience. Objects fell downward. This was obvious. This was observable. This required no explanation beyond the simple fact that things naturally moved downward toward the Earth. Philosophers and scholars had debated the nature of this downward tendency, but none had successfully created a mathematical framework that could predict and describe gravitational phenomena with precision. The universe remained fundamentally mysterious in this regard. Newton changed everything. He proposed a radical idea. Gravity is not merely a local phenomenon affecting objects near the Earth. Gravity is a universal force. It operates everywhere in the cosmos. It acts between any two objects that possess mass, regardless of how far apart they are. This force follows a simple mathematical relationship. It is proportional to the product of the two masses, and inversely proportional to the square of the distance between them. This mathematical relationship is elegant in its simplicity. It means that if you double the mass of one object, the gravitational force doubles. If you double the distance between two objects, the gravitational force becomes 1/4 as strong. This inverse square law, as it came to be known, allowed scientists to predict the motion of planets, the orbit of the moon, the trajectory of comets. It unified terrestrial and celestial mechanics under one comprehensive framework. The apple falling in Newton's garden and the moon orbiting the Earth obeyed the same fundamental law. For more than 200 years, Newton's theory of gravity reigned supreme. It explained observations with remarkable accuracy. It allowed engineers to calculate trajectories for projectiles. It enabled astronomers to predict celestial events years in advance. It provided the mathematical foundation for the scientific revolution. And yet, by the end of the 19th century, cracks began to appear in this magnificent edifice. Mercury, the smallest planet and closest to the Sun, orbits our star at a slightly different pace than Newton's equations predicted. The difference is tiny, almost imperceptible, but it is measurable. It is real. Astronomers could not explain this discrepancy. They proposed the existence of another planet, even closer to the Sun, that might account for the anomaly. They searched for this planet. They never found it. Then, in 1905, Albert Einstein published a paper that would eventually revolutionize physics even more profoundly than Newton's work had done centuries before. Einstein proposed that gravity is not actually a force in the Newtonian sense. Instead, massive objects bend and curve the fabric of space and time itself. Imagine space not as empty void, but as a flexible, elastic medium. Place a heavy object within it, and space curves around that object. Other objects moving through this curved space follow paths that appear to be influenced by a force, but they are actually following the straightest possible paths through curved geometry. This concept of curved space-time is difficult to visualize, but imagine a rubber sheet stretched flat. Place a bowling ball upon it, and the sheet curves downward around the ball. Now roll a marble across the sheet. The marble's path will curve toward the bowling ball, not because the bowling ball is pulling it with a force, but because the marble is following the contours of the curved surface. This is how Einstein's general relativity describes gravity. Objects do not pull on each other across empty space. Rather, massive objects warp the geometry of space-time itself, and other objects follow the curves in this warped geometry. Einstein's theory made a prediction that Newton's theory could not make. It predicted that Mercury's orbit would precess or rotate slightly by a specific amount. When astronomers measured Mercury's actual precession, they found that Einstein's prediction matched reality with extraordinary precision. Where Newton's theory fell short, Einstein's theory succeeded. This was a triumph of theoretical physics, a demonstration that mathematics could reveal truths about reality that observation alone could not reveal. Moreover, Einstein's theory predicted something even more remarkable. Light itself should be bent by gravity. Light has no mass, yet it should still be affected by the curvature of space-time caused by massive objects. In 1919, during a solar eclipse, British astronomer Arthur Eddington led an expedition to photograph stars that appeared near the sun's disk. If Einstein was correct, the sun's gravity should bend the starlight passing near it, making the stars appear slightly displaced from their normal positions. Eddington's measurements confirmed this prediction. Light was indeed bent by gravity. Einstein became famous overnight. His theory was validated. For decades, Einstein's general relativity seemed to be the ultimate description of gravity. It explained phenomena that Newton's theory could not. It made predictions that were verified by observation. It was elegant, mathematically beautiful, and seemingly complete. Physicists felt confident that they had finally understood gravity at its deepest level. They believed that with general relativity, they had grasped one of the fundamental forces of nature. Yet the universe had other plans. It had other secrets still waiting to be discovered. It had mysteries that would require scientists to extend their theories even further, to propose the existence of something that contradicted their intuitions, something that would force them to confront the limits of their understanding in ways they had not anticipated. The stage was set for a discovery that would challenge everything physicists thought they knew about the cosmos. The observation: galaxies spinning faster than physics allows. Imagine you are an astronomer in the 1970s, equipped with powerful telescopes and sensitive instruments that allow you to measure the light coming from distant galaxies. You are studying a particular galaxy, measuring how fast different parts of it rotate. You measure the light emitted by gas and stars at various distances from the galactic center. From this light, you can determine their velocities. You create a graph showing velocity versus distance from the center. You expect to see a particular pattern. According to the laws of Newton and Einstein, as you move outward from the center of a galaxy, the velocity of orbiting objects should decrease. This is what we observe in our own solar system. Mercury, closest to the Sun, orbits faster than Earth. Earth orbits faster than Mars. Mars orbits faster than Jupiter. The pattern is clear and consistent. Closer objects move faster, farther objects move slower. This pattern arises directly from the mathematics of gravity. An object orbiting at a great distance from the center experiences much less gravitational pull, so it needs less velocity to maintain a stable orbit. Yet when astronomers examined the rotation curves of galaxies, they found something astonishing. The velocity of stars in the outer regions of galaxies did not decrease as predicted. Instead, the velocity remained nearly constant. Stars at the edge of a galaxy moved almost as fast as stars closer to the center. This should be impossible. The gravitational pull from the galactic center should be so weak at such vast distances that outer stars should be moving much more slowly. They should eventually escape the galaxy entirely. The implications of this observation were profound. Either the laws of gravity, which had been tested countless times and had proven reliable in every circumstance, were somehow wrong, or there was much more mass in these galaxies than could be accounted for by the visible matter. The visible stars, the gas clouds, the dust, all the luminous material that emitted or reflected light, did not provide enough gravitational pull to keep the outer stars in their observed orbits. Vera Rubin, an American astronomer, conducted extensive observations of galaxy rotation curves throughout the 1970s and 1980s. She measured dozens of galaxies and found the same pattern repeatedly. The outer regions of galaxies moved too fast. They should have been torn apart by centrifugal effects, yet they remained intact, bound together by forces that current theory could not explain. Rubin's work provided compelling evidence that something was fundamentally wrong with our understanding of the universe. The most straightforward explanation was that each galaxy was surrounded by a massive halo of invisible matter. This halo would be composed of material that did not emit light, that could not be seen with telescopes, that revealed its presence only through its gravitational effects. If such a halo existed, with a mass perhaps 5 or 10 times greater than the visible matter in the galaxy, it would provide enough gravitational pull to explain the observed rotation curves. The outer stars would be held in place by the gravity of this invisible halo. This explanation, while mathematically elegant, introduced a profound mystery. What was this invisible matter? What was it made of? How could something so massive, something that constituted the majority of the matter in the universe, remain completely undetected by direct observation? Scientists had long assumed that the universe was composed of ordinary matter, atoms made of protons, neutrons, and electrons. But if invisible matter existed in such abundance, then atoms were not the primary constituents of reality. Something else, something unknown, dominated the cosmos. The observation of anomalous galaxy rotation curves was not the only evidence pointing toward the existence of invisible matter. Astronomers studying the motion of galaxies within galaxy clusters found that the clusters were moving too fast to remain bound together by the gravity of the visible matter alone. The galaxies should have flown apart billions of years ago, yet they remained clustered together, suggesting that an invisible gravitational pull held them in place. The evidence accumulated from multiple independent observations, all pointing toward the same conclusion. The universe contained far more matter than could be seen with telescopes. Some scientists initially resisted this conclusion. They proposed modifications to the laws of gravity itself. Perhaps, they suggested, gravity behaved differently at very large scales. Perhaps Newton's inverse square law broke down when applied to galactic distances. Perhaps Einstein's general relativity required modifications to account for phenomena at cosmic scales. These alternative theories, collectively known as modified gravity theories or MOND, modified Newtonian dynamics, offered a different explanation for the observations. Instead of proposing invisible matter, they proposed invisible forces, modifications to gravity itself. Yet modified gravity theories faced their own difficulties. While they could explain some observations, they struggled with others. They could not easily account for the patterns observed in the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space. They could not explain the large-scale structure of the universe, the way galaxies were distributed in vast filaments and voids. The theory of dark matter, while deeply mysterious, proved more successful at explaining the diverse range of cosmic observations. Gradually, the scientific consensus shifted. Most astronomers and physicists came to accept that invisible matter, dark matter, was real. It was not merely a mathematical artifact or a sign that our theories needed modification. It was an actual component of the universe. It was everywhere. It shaped the structure of galaxies. It influenced the evolution of the cosmos. It was, in a very real sense, the dominant form of matter in existence. This acceptance did not come easily. Scientists are trained to be skeptical of entities that cannot be directly observed or measured. The burden of proof for the existence of dark matter was enormous, yet the evidence became overwhelming. Too many independent observations pointed in the same direction. Too many cosmic phenomena could not be explained without invoking the existence of invisible matter. Science, at its best, follows the evidence wherever it leads, even when that path is strange and counterintuitive. The invisible hand, introducing dark matter to the equation. Contemplate for a moment the profound strangeness of what we are proposing. We are saying that most of the universe is invisible. We are saying that the matter we can see, the matter that composes stars and planets and living creatures, is merely the thin foam floating on the surface of an invisible ocean. We are saying that if we could somehow make all the dark matter visible, we would see that galaxies are embedded within massive halos of this invisible substance. We would see that the universe is not as we perceive it with our telescopes and instruments. The term dark matter itself is somewhat misleading. It suggests that we are talking about matter that is dark, that is black, that is merely a darker version of ordinary matter. But dark matter is not dark in the sense that a black hole is dark. A black hole is dark because it traps light. Dark matter is invisible not because it is black, but because it does not interact with light at all. It does not emit light. It does not absorb light. It does not scatter light. Light passes through dark matter as if the dark matter were not there. Only gravity reveals the presence of dark matter. This property of dark matter makes it extraordinarily difficult to study. Our telescopes, our instruments, our entire apparatus of astronomical observation depends on light. We see the universe because light travels from distant objects to our eyes or to our instruments. We measure the properties of distant objects by analyzing the light they emit or reflect. But dark matter does not emit or reflect light. It reveals its presence only through the gravitational pull it exerts on visible matter. Imagine trying to understand the shape of a person's face while wearing a blindfold and being allowed to touch only their hair. You could feel the hair. You could sense its texture and movement, but you would have no direct knowledge of the underlying structure. You would have to infer the shape of the face based on how the hair moved and fell. This is analogous to how we study dark matter. We cannot see it directly. We can only infer its presence and properties based on how it affects visible matter through gravity. When scientists refer to dark matter, they are actually referring to multiple possible candidates. They do not know what dark matter is made of. Several theoretical possibilities exist. The most popular candidates are WIMPs, which stands for weakly interacting massive particles. These would be particles that rarely interact with ordinary matter, that have significant mass, and that are produced in sufficient abundance to account for the observed dark matter density in the universe. WIMPs would pass through ordinary matter almost unimpeded, like ghosts walking through walls. Billions of WIMPs might be passing through your body right now, having no effect on you whatsoever. Invisible and undetectable. Another candidate is axions, hypothetical particles proposed to solve a different problem in physics, but which could also account for dark matter. Axions would be incredibly numerous, but extremely light, each one carrying almost no mass. Trillions upon trillions of axions would be needed to account for the dark matter density. Unlike WIMPs, axions would interact very weakly with light under certain conditions, which offers a potential method for detecting them. There are also more exotic candidates. Primordial black holes, formed in the very early universe, could constitute dark matter. Sterile neutrinos, hypothetical particles that interact even more weakly than ordinary neutrinos, could be dark matter. There are dozens of proposed candidates, each with different properties, each requiring different detection methods. The existence of so many possible candidates reflects the profound uncertainty that surrounds dark matter. Scientists do not know what it is. They have narrowed the possibilities somewhat through various observations and experiments, but the fundamental mystery remains. We know that dark matter exists based on the gravitational effects we observe. We know that it comprises most of the matter in the universe, but we do not know what it is made of. This ignorance is humbling. It reminds us that despite all our scientific progress, despite our sophisticated instruments and brilliant minds, there are still fundamental aspects of reality that elude our understanding. We can measure the effects of dark matter. We can calculate how much dark matter exists in different regions of space. We can model how dark matter influences the motion of galaxies. But we cannot answer the most basic question. What is it? The history of science is filled with examples of invisible entities that were eventually understood. In the 19th century, atoms were invisible, but scientists eventually developed methods to study them. Electromagnetic waves were invisible, but scientists learned to detect and measure them. Subatomic particles were invisible, but scientists built machines to create and observe them. In each case, what was once invisible became visible through technological innovation and theoretical insight. Perhaps dark matter will follow the same pattern. Perhaps future generations of scientists will develop technologies that allow them to detect dark matter directly. Perhaps they will understand its nature and integrate it into a more comprehensive theory. Or perhaps dark matter represents a fundamental limit to human knowledge, something that will always remain partially mysterious. Either way, the pursuit of understanding dark matter continues. It drives research in particle physics, in cosmology, in astrophysics. It inspires scientists to develop new instruments, new theories, new ways of thinking about the universe. The introduction of dark matter into our understanding of the universe was not a moment of triumph, but a moment of humility. It was an acknowledgement that our theories, while powerful and successful, were incomplete. It was an admission that the universe was far stranger than we had imagined. It was an invitation to expand our minds, to embrace mystery, to continue seeking understanding even when that understanding seems impossibly distant. The detection paradox, searching for something we cannot see. Imagine the challenge facing physicists who accepted the existence of dark matter. They needed to find it. They needed to detect it. They needed to measure its properties. But how do you detect something that does not emit light, does not absorb light, does not interact with light in any way? How do you search for an invisible entity that passes through ordinary matter almost unimpeded? This is the fundamental paradox of dark matter research. The very properties that make dark matter so abundant and so important for understanding the universe are the same properties that make it incredibly difficult to detect. A particle that interacts weakly with ordinary matter is precisely a particle that will leave few traces in our detectors. A particle that does not interact with light is a particle that cannot be observed with telescopes or any light-based instrument. Scientists have developed several approaches to detect dark matter. The most direct approach involves building underground detectors that are sensitive to the rare interactions between dark matter particles and ordinary atomic nuclei. These detectors are typically placed deep underground, in mines or caverns, to shield them from cosmic rays that would otherwise create false signals. The detectors contain extremely sensitive instruments that can register the tiny recoil of an atomic nucleus struck by a dark matter particle. The sensitivity required for these detectors is extraordinary. A dark matter particle passing through Earth would interact with ordinary matter perhaps once in every billion years. To have any hope of detecting such rare events, scientists must build detectors containing enormous quantities of material and monitor them for years, looking for the telltale signature of a dark matter interaction. Several such detectors have been constructed around the world. The LUX detector, located deep in a mine in South Dakota, used a tank of liquid xenon to search for dark matter. The Xenon experiment, located in a laboratory beneath the Gran Sasso mountain in Italy, used similar technology. The Super CDMS detector, located in a mine in Minnesota, used semiconductor crystals cooled to extremely low temperatures to detect dark matter interactions. These experiments represent the cutting edge of dark matter detection technology. Yet despite decades of searching, despite the construction of increasingly sensitive detectors, no definitive detection of dark matter has been made. Scientists have found hints, tantalizing signals that might indicate dark matter, but none that have been confirmed and accepted by the scientific community. The detectors have established limits on the properties that dark matter particles could have. They have ruled out certain possibilities, but they have not definitively identified what dark matter is. This lack of detection raises troubling questions. If dark matter is so abundant, if it is everywhere, if billions of dark matter particles are passing through our bodies every second, why is it so difficult to detect? Scientists have proposed several explanations. Perhaps dark matter particles interact with ordinary matter even more weakly than theoretical predictions suggest. perhaps dark matter is not composed of particles at all, but of some other form of matter, such as primordial black holes. Perhaps the experiments have simply not yet achieved the sensitivity required to detect dark matter. The lack of detection also raises a more philosophical question. How confident should we be in the existence of dark matter if we have never directly observed it? We infer its existence from gravitational effects, from the way galaxies rotate, from the way galaxy clusters move. But inference is not the same as direct observation. Scientists are trained to be skeptical of entities that cannot be directly detected and measured. Yet the gravitational evidence for dark matter is so overwhelming, so consistent across multiple independent observations, that most scientists remain convinced of its existence, even though it has never been directly detected. This situation is unusual in the history of science. Typically, scientists propose a hypothesis, make predictions based on that hypothesis, and then test those predictions experimentally. If the predictions are confirmed, the hypothesis is accepted. If they are contradicted, the hypothesis is rejected. But dark matter is different. The hypothesis was proposed to explain observations. The predictions made based on this hypothesis, such as the existence of dark matter halos around galaxies, have been confirmed. Yet the most direct test of the hypothesis, the detection of dark matter particles themselves, has not been successful. Some scientists interpret this situation as evidence that dark matter theory is correct, but simply difficult to test experimentally. Others interpret it as evidence that something is fundamentally wrong with dark matter theory. They point out that dark matter is, in a sense, a placeholder, a name we give to the invisible substance that we know must exist, but do not understand. They suggest that perhaps a better theory, one that does not require invisible matter, might eventually be developed. Alternatively, perhaps the problem lies with our detection methods. Perhaps dark matter particles interact with ordinary matter in ways that our current detectors are not designed to measure. Perhaps we need to develop entirely new detection technologies that would be sensitive to these interactions. Scientists are actively pursuing multiple detection strategies. Some are looking for dark matter particles directly. Others are looking for the products of dark matter particle annihilation. Still others are using gravitational waves, which are ripples in space-time itself, to search for signatures of dark matter. The detection paradox reflects a deeper truth about science. Scientific knowledge is built on evidence, but evidence is always filtered through our instruments, our methods, our theoretical frameworks. We do not have direct, unmediated access to reality. We always observe reality through the lens of our apparatus. Dark matter represents a case where we are highly confident that something exists, based on the gravitational evidence, yet we struggle to directly observe it with our instruments. This situation reminds us that the pursuit of scientific truth is more complex than it might initially appear. It requires not only careful observation and measurement, but also theoretical insight, creativity, and the willingness to pursue understanding even when direct evidence remains elusive. The gravitational lens, how light bends around hidden mass. Now we turn to one of the most elegant and compelling pieces of evidence for dark matter. We turn to an effect that Einstein himself predicted, an effect that reveals the presence of invisible matter by showing how light bends around it. We turn to gravitational lensing, one of the most beautiful demonstrations of how gravity shapes the universe. Imagine standing before a massive lens made of glass. Light passes through the lens and bends, refracting as it travels through the curved glass. Objects viewed through the lens appear distorted, magnified or displaced from their actual positions. The glass bends the light because of its density, because of the material it is made of. Now imagine a similar effect happening in space, but instead of glass, the bending is caused by the curvature of space-time itself, created by massive objects. According to Einstein's general relativity, massive objects bend the space and time around them. Light, traveling through this bent space, follows a curved path. The more massive the object, the more severely it bends space, and the more dramatically it bends the light passing near it. This effect, predicted by Einstein and confirmed by observations of starlight bending around the sun during solar eclipses, is called gravitational lensing. Gravitational lensing can reveal the presence of invisible matter. Consider a distant galaxy whose light travels across the universe toward us. Between that distant galaxy and Earth, suppose there exists a massive cluster of galaxies. The gravity of this cluster bends the light from the distant galaxy. When we observe the distant galaxy, we see its light distorted by the gravitational field of the intervening cluster. The light might be magnified, making the distant galaxy appear brighter than it would otherwise. The light might be split into multiple images, so we see the same galaxy in multiple places on the sky. The light might be smeared into an arc or ring shape, creating patterns of extraordinary beauty. By analyzing the pattern of this gravitational lensing, astronomers can determine how much mass the intervening cluster contains. They can map the distribution of this mass throughout the cluster. Here is where dark matter becomes visible, in a sense. When astronomers calculate how much mass is needed to produce the observed lensing pattern, they find that far more mass is required than can be accounted for by the visible matter. The stars, the gas, the dust, all the luminous material in the cluster does not provide enough gravitational pull to create the observed lensing. The missing mass must be dark matter. Gravitational lensing has become one of the most powerful tools for studying dark matter. Astronomers observe the light from distant galaxies distorted by the gravity of massive structures between us and those galaxies. They use this distortion to map the distribution of dark matter. They have created detailed maps of dark matter distribution in galaxy clusters. They have discovered that dark matter is not uniformly distributed, but is concentrated in certain regions, with voids and filaments creating a cosmic web structure. One particularly striking example of gravitational lensing involves the Bullet Cluster, the remnants of a collision between two massive galaxy clusters. When these clusters collided, the ordinary matter in them, composed of gas and stars, collided and was slowed by the collision. It piled up in the middle, creating a region of high density. But the dark matter in the two clusters passed through each other almost unimpeded. The dark matter from one cluster continued moving in one direction, while the dark matter from the other cluster continued moving in another direction. This separation between the ordinary matter and the dark matter is visible through gravitational lensing. The lensing patterns show that the center of mass, which is where most of the mass is located, is offset from the visible matter. This offset is direct evidence that dark matter is real and distinct from ordinary matter. Gravitational lensing also provides a method for detecting dark matter that does not require building sensitive detectors or looking for rare particle interactions. Astronomers simply observe the light from distant objects and analyze how it has been bent by gravity. This method is indirect, in that we are not directly detecting dark matter particles, but it is elegant and powerful, providing information about dark matter that cannot be obtained any other way. The beauty of gravitational lensing lies in its simplicity and directness. We observe the effect of dark matter on light. Light is bent by gravity. The bending reveals the presence and distribution of mass. By analyzing the bending, we learn about dark matter. No exotic detectors are required. No particle accelerators are needed. We simply look at the universe and read the message that gravity has written across the light from distant galaxies. Moreover, gravitational lensing allows astronomers to observe dark matter in regions of space where other methods would not work. They can study dark matter in galaxy clusters, in distant parts of the universe, in regions where no other observations would be possible. Gravitational lensing has revealed that dark matter is not merely present in galaxies, but is distributed throughout the universe on the largest scales. The images created by gravitational lensing are often strikingly beautiful. Distant galaxies distorted into arcs and rings by the gravity of intervening clusters. Multiple images of the same galaxy arranged in a symmetrical pattern. These images are not merely pretty pictures, they are data. They contain information about the distribution of dark matter. They are messages from the universe about its own structure and composition. Gravitational lensing exemplifies something important about the search for dark matter. We cannot directly see dark matter, but we can observe its effects. We can see how it bends light. We can see how it influences the motion of galaxies. We can see how it shapes the structure of the universe. Through careful observation and analysis, We can learn about dark matter without ever directly detecting a dark matter particle. The invisible becomes visible through the traces it leaves on visible matter. The cosmic web, dark matter as the universe's hidden architecture. Allow yourself to imagine the universe at the largest scales, not the scale of individual galaxies or even galaxy clusters, but the scale at which we can see the entire observable universe. At this vast scale, the distribution of galaxies is not random. Galaxies are not scattered uniformly throughout space. Instead, they are arranged in a structure of extraordinary complexity and beauty. They form filaments, sheets, and voids. They cluster into superclusters. They create a pattern that resembles a cosmic web or foam. This cosmic web structure was not created by gravity, acting on ordinary matter alone. If only ordinary matter existed, galaxies would not form the patterns we observe. The universe would look different. The large-scale structure of the cosmos is shaped by dark matter. Dark matter provides the gravitational scaffolding upon which galaxies are constructed. Ordinary matter, the stars and gas and dust, collects in the regions where dark matter is concentrated. Imagine dark matter as an invisible framework, a three-dimensional lattice extending throughout the universe. Galaxies form at the nodes of this lattice, at the points where dark matter is most concentrated. The filaments of the lattice, the regions of slightly higher dark matter density connecting the nodes, contain streams of galaxies. The voids between the filaments, regions of extremely low dark matter density, contain very few galaxies. The cosmic web is the visible manifestation of the dark matter distribution. This understanding comes from a combination of observations and computer simulations. Astronomers have mapped the positions of millions of galaxies, creating three-dimensional models of the universe's large-scale structure. They have observed that galaxies are indeed arranged in filaments and sheets, with vast voids in between. Simultaneously, physicists have created computer simulations that model how the universe evolves under the influence of gravity, starting from the conditions of the early universe and progressing to the present day. These simulations include both ordinary matter and dark matter. When physicists run these simulations, they find that the resulting structure matches the observed cosmic web remarkably well. The agreement between observations and simulations is not perfect. Some details do not match. Some aspects of galaxy formation are not yet fully understood. But the overall agreement is impressive. It provides strong evidence that our understanding of dark matter and its role in shaping cosmic structure is basically correct. The cosmic web reveals something profound about the universe. The visible universe, the stars and galaxies and clusters that we can observe with telescopes, is merely the thin visible layer of a much vaster structure. Beneath and around this visible layer lies the dark matter web, shaping and controlling the distribution of visible matter. The visible universe is, in a sense, the foam on the surface of the dark matter ocean. This realization has transformed our understanding of cosmic evolution. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly. There were tiny density fluctuations, regions that were slightly denser or less dense than average. These tiny fluctuations were the seeds from which all cosmic structure would grow. Gravity amplified these fluctuations. Regions that were slightly denser became denser. Regions that were slightly less dense became less dense. Over billions of years, this process created the cosmic web we observe today. But here is the crucial point. Ordinary matter alone could not have created this structure in the time available. Ordinary matter moves slowly through space, held back by pressure forces. For ordinary matter to collapse under gravity and form structures, it needs a long time. The universe is only about 13.8 billion years old. In that time, ordinary matter could not have collapsed enough to form the observed cosmic structure. Dark matter, however, does not experience pressure forces. It interacts with ordinary matter only through gravity. Dark matter can collapse under gravity much more rapidly than ordinary matter can. The dark matter web formed first, providing the gravitational scaffolding. Ordinary matter then flowed into the regions where dark matter was concentrated, forming galaxies and galaxy clusters. Without dark matter, the universe would not have had time to develop the structure we observe. The cosmic web is constantly evolving. Filaments are feeding material into the nodes where galaxy clusters form. Voids are expanding, becoming even less dense. The structure is not static but dynamic, changing slowly over cosmic timescales. Galaxies are moving along the filaments, flowing toward the densest regions. The universe is a dynamic system, constantly evolving under the influence of gravity and dark energy. Understanding the cosmic web has profound implications for cosmology. It tells us that the universe is structured, that there is order and pattern in the distribution of matter. It tells us that dark matter plays a central role in creating this structure. It tells us that the visible universe is intimately connected to the invisible dark matter universe. We cannot understand the cosmos without understanding dark matter. The cosmic web also raises questions about the future of the universe. How will the structure continue to evolve? Will the voids continue to expand? Will the filaments continue to feed material into clusters? Will the universe eventually reach some final state? Or will it continue evolving indefinitely? These questions are still being investigated by cosmologists. The answers depend on understanding dark matter and dark energy, both of which remain partially mysterious. The alternative whispers. When scientists question their own theories, even as the scientific consensus has shifted toward accepting dark matter, not all scientists have abandoned doubt. In the quiet chambers of research institutions and universities around the world, some physicists continue to question whether dark matter truly exists. They propose that perhaps the problem lies not with the missing matter, but with the laws of gravity itself. They suggest that perhaps Einstein's general relativity, while extraordinarily successful at explaining many phenomena, requires modification at the largest cosmic scales. The most developed alternative to dark matter is called modified Newtonian dynamics, or MOND. This theory was proposed in 1983 by Israeli physicist Mordechai Milgram. MOND suggests that at very low accelerations, the kind experienced by stars at the edges of galaxies, gravity behaves differently than Newton and Einstein predicted. Instead of following the inverse square law, gravity might follow a different mathematical relationship at these low accelerations. The appeal of MOND is its simplicity. Rather than proposing the existence of invisible matter that we cannot detect, MOND suggests that we modify our understanding of gravity itself. If MOND is correct, then the universe contains no dark matter. The missing mass that astronomers observe is not actually missing. The observations are perfectly explained by modified gravity. MOND has some successes. It can explain galaxy rotation curves without invoking dark matter. It can explain some aspects of galaxy cluster dynamics. It has motivated research into alternative theories of gravity. Some scientists find MOND appealing precisely because it does not require the existence of undetected matter. However, MOND faces significant challenges. It struggles to explain the cosmic microwave background radiation, the afterglow of the Big Bang that fills all space. It cannot easily account for the large-scale structure of the universe, the cosmic web of filaments and voids that we observe. It makes predictions for certain phenomena that are not confirmed by observations. For these reasons, most physicists have not accepted MOND as a replacement for dark matter theory. Nevertheless, the existence of alternative theories like MOND serves an important function. It reminds us that science is not dogmatic. It reminds us that even widely accepted theories can be questioned. It reminds us that scientists should remain open to alternative possibilities, even when consensus has formed around a particular explanation. The pursuit of truth requires maintaining a degree of skepticism, even toward established ideas. There are other alternative theories besides MOND. TVIS, or tensor vector scalar gravity, is a relativistic theory that attempts to incorporate some of the ideas of MOND while remaining consistent with Einstein's framework. Other scientists have proposed that gravity might be modified due to extra dimensions, or that the universe might be structured differently than we currently believe. These theories represent the diversity of approaches that scientists take when confronted with puzzling observations. The existence of these alternatives raises important questions about the nature of scientific knowledge. How do we decide between competing theories when both can explain some observations but not others? How much evidence do we need before we accept a theory as true? How do we balance the principle of parsimony, the idea that simpler explanations are preferable, against the principle of empirical adequacy, the idea that a theory should explain all available observations? Scientists grapple with these questions constantly. They debate the merits of dark matter theory versus modified gravity theories. They propose new observations that might distinguish between competing theories. They develop more sophisticated versions of existing theories to address problems and inconsistencies. This process of debate and refinement is essential to the scientific enterprise. It prevents science from becoming dogmatic. It ensures that science remains responsive to evidence and open to new ideas. Moreover, the existence of alternatives like MOAND has motivated improvements in dark matter theory itself. Scientists working on dark matter have been forced to become more precise in their predictions, to address criticisms, to develop more sophisticated models. The competition between dark matter theory and alternative theories has advanced our understanding of both approaches. Even if MOND and other alternatives ultimately prove to be incorrect, they will have served a valuable purpose by pushing dark matter theory to become more rigorous and comprehensive. The scientific community has tentatively accepted dark matter as the most likely explanation for the observations, but this acceptance is provisional, conditional on future evidence. If new observations were made that contradicted dark matter theory while supporting modified gravity theories, scientists would be willing to change their minds. This willingness to revise beliefs in light of new evidence is one of the defining characteristics of science. The particle hunt, laboratories listening for dark matter's faint signal. Picture a laboratory buried deep beneath the Earth. The laboratory is located in a mine, perhaps 1,000 meters below the surface. The rocks surrounding the laboratory shield it from cosmic rays, high-energy particles that constantly bombard the Earth's atmosphere from space. Inside the laboratory, sensitive instruments wait in darkness, listening for a signal that may never come. These instruments are searching for dark matter. The laboratories conducting dark matter searches represent some of the most sophisticated scientific facilities in the world. They contain instruments that are sensitive to the tiniest interactions between dark matter and ordinary matter. They are cooled to extremely low temperatures, near absolute zero, to reduce thermal noise that might obscure the signal they are seeking. They are surrounded by shielding to block radiation that might create false signals. Every aspect of their design is optimized for the detection of an elusive particle that may pass through ordinary matter almost unimpeded. One of the most successful dark matter detection experiments is the LUX experiment, which operated in the Sanford Underground Research Facility in South Dakota. LUX used a tank containing 700 kilograms of liquid xenon. Xenon is a noble gas that is liquid at extremely low temperatures. When a dark matter particle collides with a xenon nucleus, the collision produces a faint flash of light and a small recoil of the xenon nucleus. Sensitive light detectors surrounding the tank detect these faint flashes. The experiment ran for several years, accumulating data that could potentially reveal dark matter. Despite the sophistication of LUX and other experiments, no definitive dark matter signal has been detected. The experiments have found no events that cannot be explained by known sources of radiation. They have established limits on the properties of dark matter particles, ruling out certain possibilities. But they have not achieved the goal of directly detecting dark matter. The lack of detection has led some scientists to reconsider their assumptions. Perhaps dark matter particles are much rarer than theoretical predictions suggest. Perhaps they interact with ordinary matter even more weakly than expected. Perhaps the detectors need to be even more sensitive. Or perhaps dark matter is not composed of particles at all, but takes some other form. Scientists are developing new detection technologies to address these possibilities. Some experiments are searching for different types of dark matter candidates using different detection methods. For example, experiments like ADMX are searching for axions using sensitive electromagnetic detectors to look for the conversion of axions into photons. Other experiments are searching for dark matter using gravitational wave detectors, looking for signatures of dark matter interactions or dark matter-related phenomena. The search for dark matter represents a remarkable commitment of scientific resources and human effort. Billions of dollars have been spent on dark matter research. Hundreds of scientists around the world are dedicated to the search. Laboratories have been built in the most remote and inaccessible locations. All of this effort is directed toward finding a particle or understanding a phenomenon that may or may not exist, that we have never directly observed, that we cannot be absolutely certain about. This commitment reflects the importance that scientists place on understanding dark matter. They recognize that dark matter is crucial for understanding the universe. They understand that the particle or phenomenon responsible for dark matter effects is likely to reveal new physics beyond our current understanding. The search for dark matter is not merely an academic exercise. It is a quest to understand the fundamental nature of reality. The challenges facing dark matter detection are formidable. The rarity of dark matter interactions means that detectors must run for a long time to accumulate sufficient data. The sensitivity required means that even tiny sources of noise can create false signals. The backgrounds, the various sources of radiation and other signals that are not dark matter, must be carefully understood and subtracted from the data. All of this makes dark matter detection an extraordinarily difficult experimental challenge. Yet scientists persist. They continue building more sensitive detectors. They continue developing new detection methods. They continue analyzing data from existing experiments. They continue because they believe that dark matter is real and important. They continue because they believe that eventually, through persistent effort and technological innovation, dark matter will reveal itself. They continue because the pursuit of understanding, even when that understanding seems impossibly distant, is what drives human science forward. The philosophical turn. What does it mean to believe in the invisible? We arrive now at a question that transcends physics and enters the realm of philosophy. What does it mean to believe in something that cannot be observed, cannot be touched, cannot be measured directly? What does it mean for science to postulate the existence of an invisible entity and then to structure an entire framework of understanding around it? These are not merely technical questions about dark matter. They are fundamental questions about the nature of scientific knowledge and the nature of belief itself. Throughout history, science has made remarkable progress by focusing on the observable and measurable. The scientific revolution began when scientists like Galileo and Newton turned away from abstract philosophical speculation and focused on careful observation and measurement. This empirical approach transformed human understanding of the natural world. It led to the development of technologies that have improved human life immeasurably. It established science as the most reliable method we have for understanding reality. Yet the case of dark matter presents a curious inversion of this empirical approach. We are postulating the existence of something that we cannot observe or measure directly. We are doing so based on the gravitational effects that this invisible entity produces. We are building an entire theoretical framework around the assumption that this invisible entity exists. In a sense, we are returning to a kind of abstract theorizing, albeit one grounded in careful observation and mathematical rigor. Some philosophers and scientists have questioned whether this is a healthy direction for science to take. They argue that science should restrict itself to observable and measurable phenomena. They suggest that postulating invisible entities that cannot be directly detected is a step backward, a return to the kind of abstract speculation that characterized pre-scientific thinking. They argue that we should instead modify our theories of gravity, as Mond and other alternative theories propose. Others defend the dark matter approach. They point out that science has always involved some degree of theoretical abstraction beyond what is directly observable. We cannot directly observe atoms, yet we have strong evidence for their existence and have built a comprehensive understanding of chemistry and physics based on atomic theory. We cannot directly observe electric and magnetic fields, yet we have strong evidence for their existence and have built a comprehensive understanding of electromagnetism based on field theory. We cannot directly observe the curvature of space-time, yet we have strong evidence for it and have built a comprehensive understanding of gravity based on Einstein's general relativity. In each of these cases, science postulated the existence of something that was not directly observable. In each case, the scientific community eventually developed methods to observe or measure these entities, or at least to observe their effects with sufficient precision and reliability to confirm their existence. Atoms, which were once purely theoretical, can now be imaged directly with scanning tunneling microscopes. Electric and magnetic fields can be measured with sophisticated instruments. The curvature of space-time can be observed through its effects on light and on the orbits of massive objects. Perhaps dark matter will follow the same pattern. Perhaps future generations of scientists will develop methods to directly detect dark matter particles, or will develop a more comprehensive theory that explains dark matter's nature. Or perhaps dark matter represents a genuine limit to what we can know about the universe, a boundary beyond which our observational methods cannot reach. This possibility raises profound questions about the limits of human knowledge. Is there a point at which the universe becomes fundamentally unknowable to us? Are there aspects of reality that will forever remain beyond our ability to observe and measure? Must we accept that some mysteries can never be solved, that some questions will never have answers? These are questions that philosophers have pondered for millennia. The case of dark matter gives these ancient questions a modern, concrete form. There is also a question about belief and faith. In what sense do we believe in dark matter? We believe in it because the evidence for its existence is overwhelming. The gravitational effects that dark matter produces are observed consistently across many different types of observations. The theory of dark matter is successful at explaining a wide range of cosmic phenomena. By the standards of science, dark matter is well established. Yet we do not have the kind of direct sensory evidence for dark matter that we have for, say, a table or a star. We cannot see it with our eyes, we cannot touch it with our hands, we cannot measure it with the instruments we typically use to measure matter. Our belief in dark matter rests on inference, on theoretical reasoning, on the logical conclusion that something invisible must exist to explain what we observe. This situation is not entirely unique to dark matter. Much of our scientific knowledge rests on inference and theoretical reasoning rather than direct sensory evidence. We cannot see the past, yet we believe in historical facts based on evidence and inference. We cannot directly observe other minds, yet we believe that other people have conscious experiences based on inference and analogy. We cannot directly observe the future, yet we make predictions based on our understanding of natural laws. In a broader sense, all knowledge involves some degree of inference and interpretation. We do not have unmediated access to reality. We always perceive reality through our senses, our instruments, our theoretical frameworks. The question of how much inference is acceptable in science, how much we can reasonably believe in invisible entities, is a question that has no simple answer. It requires judgment, wisdom, and a careful weighing of evidence and alternatives. The case of dark matter invites us to reflect on these broader questions about knowledge and belief. It challenges us to think carefully about what we know and how we know it. It reminds us that science, while extraordinarily powerful and successful, operates within certain limitations. It shows us that sometimes the pursuit of truth requires us to accept uncertainty, to believe in something without perfect evidence, to live with mystery while continuing to seek understanding. The future horizon. New instruments, new questions, new possibilities. Look forward now toward the future, toward the coming decades and centuries. Imagine the technologies that will be developed, the instruments that will be built, the observations that will be made. The search for dark matter will continue and will likely intensify. New experiments will be conducted, new detection methods will be developed, new data will be gathered. Some of this data may finally provide the definitive detection of dark matter that has eluded scientists for so long. One promising direction involves the construction of even more sensitive detectors. Current detectors are limited by background radiation and thermal noise. Future detectors might employ cryogenic technology to cool their sensors to even lower temperatures, reducing thermal noise. They might use larger volumes of detecting material, increasing the chances of detecting rare dark matter interactions. They might employ multiple detection methods simultaneously, cross-checking results to ensure reliability. Another promising direction involves the use of gravitational waves. Gravitational waves are ripples in space-time itself, produced by accelerating massive objects. The detection of gravitational waves, first accomplished in 2015, opened a new window on the universe. Gravitational waves carry information that light cannot convey. In principle, gravitational waves could carry signatures of dark matter interactions or dark matter-related phenomena. Future gravitational wave detectors, more sensitive than current ones, might detect signals from dark matter. The next generation of telescopes will also contribute to dark matter research. The James Webb Space Telescope, launched in 2021, can observe distant galaxies with unprecedented detail. It can measure the properties of galaxies in the early universe, providing information about how dark matter influenced galaxy formation in the past. Future ground-based telescopes, such as the Extremely Large Telescope, will observe even more distant objects and provide even greater detail. These observational advances will generate new data about dark matter. They will provide new tests of dark matter theory. They may reveal unexpected phenomena that require new theoretical understanding. The interplay between observation and theory will continue, with each informing and constraining the other. There is also the possibility that entirely new approaches to understanding dark matter will emerge. Perhaps a completely different theoretical framework will be developed that explains dark matter phenomena without requiring invisible matter. Perhaps dark matter will turn out to be something completely unexpected, something that we have not yet imagined. Science has a history of surprising us. The universe has a way of being stranger and more wonderful than our theories predict. One intriguing possibility is that dark matter might be connected to other mysteries in physics. For example, the nature of dark energy, which is causing the universe's expansion to accelerate, remains unknown. Perhaps dark matter and dark energy are related, different manifestations of the same underlying phenomenon. Perhaps understanding one will lead to understanding the other. Another possibility is that dark matter might be connected to the nature of consciousness or quantum mechanics. Some theoretical physicists have speculated about connections between dark matter and quantum phenomena. These ideas are highly speculative, but they illustrate how dark matter research might lead to unexpected insights about the nature of reality. The future of dark matter research is uncertain. We do not know what will be discovered. We do not know whether dark matter will eventually be directly detected or whether it will remain forever mysterious. We do not know whether dark matter will turn out to be a fundamental constituent of the universe or whether it will eventually be understood as a manifestation of something more fundamental. But we can be confident that the search will continue. The importance of dark matter for understanding the universe ensures that resources will be devoted to studying it. The intellectual challenge of the dark matter problem ensures that brilliant minds will continue to work on it. The profound philosophical implications ensure that dark matter will remain a topic of deep contemplation. The future horizon stretches before us, full of possibilities. Some of these possibilities may be realized, others may not. But the journey of discovery continues. The universe continues to reveal its secrets slowly and gradually. Dark matter is one of the great mysteries of our age, and the pursuit of understanding it is one of the great quests of modern science. The eternal question, living with mystery in an age of certainty. We come now to the conclusion of our exploration, not to a final answer, but to a deeper understanding of the question itself. We have journeyed through the history of gravity, from Newton's apple to Einstein's space-time. We have confronted the observations that challenged our theories. We have explored the invisible substance that scientists propose fills most of the universe. We have examined the technologies used to search for dark matter. We have contemplated the philosophical implications of believing in the invisible. And now we arrive at a place of quiet contemplation where we can reflect on what we have learned and what remains unknown. The fundamental lesson of dark matter is that the universe is far stranger and more mysterious than our everyday experience suggests. We live in a world of visible matter, of light and color and tangible objects. We naturally assume that this visible world represents the totality of reality. Yet physics reveals that the visible universe is merely a small fraction of the whole. Most of the matter in the universe is invisible. most of the gravitational influence that shapes cosmic structure comes from something we cannot see. This realization is humbling. It teaches us that our perception of reality is limited. Our senses, our instruments, our theories are all limited. There are aspects of reality that lie beyond our current ability to observe and measure. There are questions that we cannot yet answer. There are mysteries that remain unsolved. Yet this realization is also liberating. It opens up possibilities for future discovery. It invites us to imagine new technologies, new theories, new ways of understanding. It reminds us that science is not a finished edifice, but an ongoing process of discovery. It suggests that the universe is far more interesting and complex than we have yet imagined. The case of dark matter teaches us something important about how science actually works, as opposed to how we sometimes imagine it works. We often picture science as a straightforward process: observe phenomena, form hypotheses, conduct experiments, reach conclusions. But dark matter shows us that science is more subtle and complex than this simple picture suggests. Sometimes we must postulate the existence of entities we cannot observe in order to explain what we do observe. Sometimes our theories remain incomplete for decades or centuries. Sometimes we must live with uncertainty and mystery while continuing to pursue understanding. This is not a weakness of science. It is a strength. It shows that science is flexible enough to adapt to new evidence, creative enough to propose novel explanations, and honest enough to acknowledge the limits of current knowledge. Scientists are trained to be skeptical, to question, to demand evidence. Yet they are also willing to accept that some questions do not have immediate answers. They continue pursuing understanding even when certainty is not available. Living with mystery in an age of certainty is perhaps the most important lesson that dark matter teaches us. We live in an age of extraordinary technological power. We have developed instruments that can measure distances to distant galaxies, detect the faint afterglow of the Big Bang, image the surfaces of distant planets. We have built computers that can process vast amounts of data and perform calculations that would have been impossible a few decades ago. We have developed theories that explain the behavior of matter and energy with remarkable precision. Yet for all this power and knowledge, we remain confronted with fundamental mysteries. We do not know what dark matter is. We do not know what dark energy is. We do not know how consciousness arises from the physical brain. We do not know whether life exists elsewhere in the universe. We do not know the ultimate fate of the cosmos. We do not know whether our theories will eventually be superseded by more comprehensive theories. This situation might seem frustrating. We have so much knowledge, yet so many questions remain unanswered. But it is also beautiful. It means that there is always more to discover. It means that the pursuit of truth continues. It means that future generations of scientists will have the opportunity to make discoveries that we can only imagine. It means that the universe will always hold mysteries for us, always invite us to deeper understanding. The exploration of dark matter reminds us that science is ultimately driven by curiosity, by the desire to understand the world around us. This curiosity is not merely an intellectual exercise, it is deeply human. Throughout history, humans have looked up at the night sky and wondered about the nature of the stars and planets. Throughout history, humans have asked fundamental questions about the nature of reality. Throughout history, humans have pursued understanding, even when that understanding seemed impossibly distant. Dark matter is one of the great mysteries of our time. It is a question that scientists are actively pursuing. It is a challenge that will occupy researchers for years to come. It is a reminder that the universe is far more complex and wonderful than we might imagine. It is an invitation to join in the pursuit of truth, to participate in the great human quest to understand reality. As we conclude this exploration, take a moment to reflect on what you have learned. Consider how the universe you inhabit is vastly different from what you might have assumed. Consider how most of the matter in the universe is invisible to you. Consider how gravity shapes the structure of galaxies and galaxy clusters and the entire cosmos. Consider how science pursues understanding, even in the face of profound mysteries. Consider how the pursuit of knowledge continues, generation after generation, pushing the boundaries of human understanding forward. The night sky above you contains secrets that are slowly being revealed. The stars you see are embedded in halos of dark matter. The galaxies you observe are shaped by invisible forces. The universe you inhabit is far more interesting and complex than it appears. And somewhere, in laboratories around the world, scientists are continuing the search for understanding. They are listening for signals from dark matter. They are analyzing observations. They are developing new theories. They are pursuing the eternal question: what is the universe really made of? Thank you for joining me on this journey through the invisible cosmos. If this experience has brought you deeper understanding and inner peace, I would appreciate a like and subscription to Relaxing Science. Please let us know if you would like to see more content exploring the mysteries of the universe. Share with us your thoughts on dark matter, your location, and the time where you are listening. Your participation transforms this exploration into a shared moment of wonder. Until we meet again, may you continue to contemplate the mysteries of existence with curiosity, wisdom, and wonder. Total.